Now the advantages over forward elimination or forward selection of backward elimination is exactly the first point here. Now it considers complete subspaces and not just so it does not rely on the attribute independence assumption, because it really considers the complete subspace first of all, then the one minus dimensionality next subspaces and stuff like that. Yeah, so it considers complete subspaces rather than single features on their own. Yeah, that means we can also try, or at least there is a chance to consider or uncover multiple dependencies between the features. And it also can recognize and eliminate redundant features. That's what we look for actually in that case. Yeah, because we consider multiple features together. That's the point. Yeah, we cannot consider redundant or cannot find redundant features if we look at each feature individually. Obviously. Yeah. Limitations here, obviously, of course, also some limitations. The test with respect to the subspace quality typically requires much more effort, especially if you do it model-based. And all these solutions, regardless of what kind of measure you use, if it's not monotonic, you just have to apply some kind of greedy heuristic method. In that case, of course, you somehow do local decisions, locally optimal decisions, best first, so to say. Yeah, so at each step you get rid of that feature which is right now the worst one, and then you continue with the remaining features. But the decision, of course, might be only locally optimal, and the global optimal subspace might be missed by that heuristics. I think that's pretty clear. Yeah, so that is actually the downside. But okay, that's how it is. And now coming to this to these measures where we have monotonic, the monotonic property, then we can apply even an exhaustive search using branch and bound, and we'll see how that works actually on the next slides. So this is the branch and bound general idea. So given a classification task, so it's supervised over the feature space F, and we have a target function for that thing, which is our evaluation measure for the subspaces for the feature space F, that is denoted as J. And again, the aim, as always so far, is we want to select the k best dimensions to learn the classifier. So we want to reduce from the number of features D, for example, reduce this feature space such that we get the k best dimensions out of F. Yeah, and now it's again a backward elimination approach, but branch and bound now guarantees really to find the optimal features set. Yeah, so it's not heuristic that probably will not find the optimal feature space because of this local optimal decisions at each step. Now branch and bound really guarantees to find the optimal feature set, but requires this monotonicity assumption. What does the monotonicity assumption actually mean? Well, the monotonicity somehow intuitively states that if you delete or get rid of a feature, the J value decreases. Yeah? The optimality, the accuracy, the goodness of the feature space decreases. Yeah, so if J is a measure that is maximized in order to be optimized, then it holds for any feature spaces X and Y, projections of the original feature space. Well, X is smaller than Y, so X is the lower dimensional feature space. If J is maximized, then it's always the case that J of X, of the smaller subspace, is smaller or equal than the quality of the higher dimensional subspace. Yeah, so and since we are maximizing J, meaning that if we get rid of features, X is the lower dimensional subspace. If we get rid of features, the quality actually decreases. And the same holds true for measures that are monotonic, that are minimized. In that case, the J function, the J value, values increase, which also intuitively means that the quality decreases. Yeah? So with decreasing dimensionality, the quality decreases, and if the quality is measured by some minimization problem, then of course it means that the actual values increase, which is a decrease in the quality, obviously. Okay, and branch and bound starts exactly as before, with the full set of features, and removes features using now typically a depth first strategy. You can use different branch and bound search strategies, but depth first is typically employed. And the trick now is that nodes whose J values are smaller or greater, depending on which one you use. If it's maximized, it's smaller. If it's minimized, it's greater. Then the current best candidate that you have, that they need not to be explored, because you know that in these sub-branches of the search tree, there cannot be any better solutions, because if you have a subspace Y, which is already worse than the best that you have, you need not to examine this Y any further, because any subspace of Y cannot be better than Y. So if Y is not the best so far, any subspaces of Y can't be better than the other one too. Yeah. So, and we see that here with an example. So here is the original feature space with 4 features. Yeah. Target dimensionality would be 1. So we want to remove 3 features. Yeah. We want to get a one-dimensional feature space out of these 4. And we use some kind of measure, and the measure has 1.0. So the measure should be optimized, maximized, sorry. And we start with 1.0, and then we generate all the 3-dimensional candidates and look at the J values. So the J value here is 1, the J value here is 7.715, the one here is 0.421, and so on and so on. Yeah? And you already see that, okay, well, in that case you don't see anything. Well, you see already that this one here is better than this one here, but we are not at the target dimensionality first. Yeah, so we need to go down to the target dimensionality in order to prune one of those candidates here. So the best candidate so far is this one here, obviously, because this has the best quality criterion right now. So we expand that further, or explore that further. So we generate all the 2-dimensional projections, which are those here with the corresponding J values. And since we are still not at the target dimensionality, so we still have to explore one of those 3 candidates here, and this one is the one with the best J values so far. So we explore this one here and end up in those 2 candidates, which are and the best one here is this one here, and that gives us the current bound for that has to be beaten, so to say. Yeah. So if we look at that bound, we can immediately see, well, this one here is already worse than this one here. So we can safely prune that. We need not to explore any subspace of this one here. And the same holds true with this one here. And the same holds true with this one here. So 0.5 is smaller than 0.62. And we need not to explore this one here for the same reasons. So the only thing that remains where something can be, where projections can be that are better is a projection of this one here. So we can prune all those guys and try to explore this candidate further. So we'll have a look at these 2 subsets here, because the others are already pruned, or the other one is already pruned. So this one here and this one here are also worse than this one here, the current best one. So we know that down here there are no one-dimensional projections of those 2-dimensional projections that will be better than this one here, because we know that the J values only decrease. That's the monotonicity criterion. So we will get this one here as the final result. And that's actually the idea of the branch and bound. And we'll have an example of monotonic behaving quality criterion on the next slide.